Okay, so in this video, I'm going to be talking about beam problems. Specifically, I'm looking at this question 3 from the 2018 exam, but all the concepts that I use, I'm going to go through this one in depth, but all the concepts that I use should be applicable to any beam problem that you're going to get. And I'm going to go through parts A, B, and C. So I'm going to use the whiteboard feature, but before I do that, I just want to go through what they're actually telling us with this drawing. So if we look at it, we've basically got a point load and a point moment at this point B. I think they forgot to label it. We've got this rectangularly distributed load of 800 pounds per feet. And then we know, looking at these supports, we have a pin at A, so that's going to be an AY and an AX. And we've got a roller at E, so we're going to have an EY. So this is more or less what the free body diagram is going to look like when we redraw it. What they're actually asking us for in this problem is they're saying calculate the support reaction. So that's finding that AY, AX, and EY that we talked about. They're asking for what's going to be the shear force and bending moment equations or expressions between points C and D. So if we were to cut the beam here or here or here, what are our shear force and bending moment equations looking like? And then the last piece, they say, let's draw the shear and bending moment diagrams for the beam. They're asking us to label our values. So I am going to share the whiteboard feature. So perfect. So my first step when I'm drawing this problem is I'm going to redraw my free body diagram, especially because we don't have it to reference. So here's my beam. I'm going to have an AY, an AX. I'm going to have an EY. Then I'm going to have that point load. I'm going to have that point moment. I'm going to have the distributed moment. This will obviously look different depending on what beam you're actually looking at, but the general concept should stay the same. So for our next step, I'm going to say, hey, what are my support reactions? This AX, AY, and EY. Start easy. Summation of forces in the X is equal to 0 is just equal to AX, or AX is equal to 0. Now I'm looking and I'm saying, okay, I have two unknown forces acting in the Y direction, so I can't just use summation of forces in the Y. Instead, I'm going to take a moment. If I say summation of moment about point A being equal to 0, I'm able to say EY times 20 minus 800 times 7, which is the magnitude of this distributed load. And then I have to multiply it by the distance it's acting at away from point A. So that's going to be 9 plus 7 halves, because we know rectangular loads just act right in the center. And I'm also going to subtract 3,000 times 5 from the point load. This ends up telling me that EY is equal to 3,850 pounds. So find that last support reaction. I can just say, hey, let me take a summation of forces in the Y direction. And that's just going to be AY plus EY minus that point load minus the value or the magnitude of the distributed load. It was just 800 times 7, and that tells me that AY is equal to 4,750 pounds. So that's part A done. Check. We found our support reactions. Now for part B, they're asking us for expressions for shear and bending between points C and D. So what I'm going to do on this page is I'm just going to draw my free body diagram for my beam, and then on the next page we'll actually look at writing equations. So I always redraw for this problem because for me it makes it way easier to picture. I would definitely recommend it. So the forces I'm actually going to have acting on this beam, I'm going to have that AY that I just found acting on the left end, this point A down here. I'm going to have that 3,000 pound point force, and I'm going to have that 8,000 pound foot moment on here. And then at this end, I'm going to have part of my total distributed load, right? So this isn't technically the whole thing. It's only going to be for one specific part. And then the forces I'm actually looking for, which is the V and the bending moment. my shear force and bending moment that I'm actually going to solve for. It's convention to draw them pointing in these directions. So you have your shear force pointing down and your bending moment pointing counterclockwise. Technically, if you drew them reversed, as long as you were consistent with your signs, you would be okay, but I would recommend drawing them this way. The other thing that we have to think about is how are we defining distances on this beam? So the total distance is going to be x, right? And then within here, we know these distances. So we know that this is 5 feet, we know this is 4 feet, and then we don't know this distance. It could be a range of values between where point C is and where point D is. So now we've got that diagram, we can move on to actually trying to figure out what our shear force and bending moment are. So for the shear force, I'm just going to say, okay, let me look at a summation of forces in the y. It's going to be equal to 0. And our first 3 forces are relatively simple. We've got our shear force pointing down. We've got that point load of 3,000. And we've got plus AY. And these won't change no matter where we are in terms of an X distance for this beam. Those are always consistent. The load that will change is due to that distributed 800 pound per foot load. So we've got minus 800. And now we just have to think about what that actual distance is. And what that distance will be is it'll be the total distance minus 9. So if I were to be able to go back and look at the drawing, you would see, oh, okay, that's just the section of beam where the 800 pound per foot load is acting, right? So from here, I basically just want to rewrite this and plug in what AY actually is. So I'd be able to get that V is equal to 1750 minus 800 times X minus 9. You technically could distribute this in, simplify, rewrite. There's no need to, if you ask me. It doesn't make it any easier to read, and it's not like you're necessarily actually plugging in. So it's not something you have to worry about. So now I'm going to look at the moment, which is going to be equal to 0. And the place that I'm actually taking this moment is the end of the beam, right? So if I'm able to go back to my last drawing, you can see here, the point that I'm actually taking the moment about is the point right at the end of the beam, right here, right? This point I just drew in green is where I'm taking the moment about. So that's where we need to measure our distances from. So if I go back to the calculation, we can start with kind of the simpler ones, the more straightforward ones. We've got that moment, the bending moment that we're actually solving for. It's positive in this case because we have it drawn, so it's going counterclockwise. We're going to subtract the moment due to AY, and the distance AY away, the distance that AY is away from the end of the beam is just the total distance of the beam, right? So times X. Now we're going to include that point moment in this case, and it's going counterclockwise. So we're just going to say plus 8,000. And now this is where it gets a little trickier. We just have to put a little more thought into it. So because of that point load, we're going to have the 3,000 pound load, and its distance away is going to be the length of the total beam minus 5. If we think about the picture, total length of the beam is X. The distance that the 3,000 pound force is away from the left-hand side is 5. That's how we get our X minus 5. And then we'll also have the distributed load. So we need to know the magnitude of the load, which is what we talked about up here, right? So we have 800 times X minus 9. But now we have to think about the distance away. And it's basically going to be half of what the load covers. So we'll have that X minus 9, and we'll just divide it by 2. So this can be simplified into being 800, it can be simplified into being 400 times X minus 9 squared, right? And that's just by multiplying through. But what we can end up doing is we can rearrange this equation as well, so that we're able to say that moment B is equal to 4,750 X minus 8,000 minus 3,000 times X minus 5 minus 400 X minus 9 squared. So this is part B. This is what they're asking for. And now comes into I wouldn't necessarily call it the hardest, but probably the most time-consuming part of this problem, where we're being asked to draw our shear force and bending moment diagrams. So how I'll always start these is I will redraw my beam and use that to base my distances on my actual graphs. Just for reference, this is going to be where the 3,000-pound force is acting. This is going to be where my distributed load is acting. There's technically the moment at this point as well. And then I've got my EY, my AY. Okay. So from here, I'm going to say this is going to be where I draw my shear force. This is going to be where I draw my bending moment. I'm drawing them right on top of each other because I know that they're related. And then I'm also going to do, trying to figure out the best way to do this. I'm going to do little dash lines, which hopefully won't be too confusing when I start drawing, because those are going to help show us, that was strange, I don't know why those ones are blue, which are going to help show us what our, like where we're kind of spacing everything, right? So for shear force, these are a lot easier to tell just by looking at the graph. So here's more or less how you can think. You can say, okay, if I look at this end and I start at this end right here, you can see I start at this end, I'm basically going to add this AY and get bumped up to there. And then the entire time I go over to here, nothing's changing, right? So what I end up getting is I would say I start at what AY is, which is 4750. I'm not writing it just because I don't have enough space, but then we'll just go straight until we hit the point with this point load, but then it's the same thought process. So we've got this load just pointing right down. So it's going to drop us down the magnitude of that load, which is 3,000. So down here, we're looking at 1750. But once again, nothing's changing in this section of the beam in terms of shear force. So we just continue sideways. Boom. And then here, if we think about this, now we've got a rectangularly distributed load. So the load is going to be changing in a linear fashion, basically. It's going to be going downward. And we know that the total magnitude that we're going to go downward is 800 times 7, right? So I'm going to take this 1750 that I have here, where I've got 1750 for this. I'm going to subtract 800 times 7, and that's going to get me to negative 3850. So I know as I draw this line, I'm going to end up at negative 3850. Nothing's going on in that last section of the beam until we hit EY, which bumps us back up to 0 at the end, right? So this is what our shear force diagram should look like. Easy. So now when we go to draw the moment, we have to remember what the relationship between these are. So the area under the shear force graph is going to be equal to the change in moment, right? So in this case, we want to find the area under that first section that I shaded in yellow, and we know moment starts at 0, and then it's going to go up in a linear fashion to, I got 23,750 for my value. Now we're going to drop according to this point moment. The reason that I'm subtracting is because of its direction. So yes, so the way you have to think about it is the fact that we're talking about the moment if we were to cut the beam section here, right? So if we cut the beam section there and the moment acting on it's positive, we're going to need less moment to create ourselves equilibrium, kind of. So that's how you have to think about it. The reason it's a straight line down is because we're looking at a point moment. From here, we can do the same thing, figure out the area under this part of the graph, and we will continue with our linear increase to whatever point we're able to find. I'm going to draw a little dash line down from this point where shear crosses the x-axis, because we know when shear crosses the x-axis, that indicates a turning point of our moment graph. So what we would do here, or what I would do here, is I would say, hey, what actually is this distance? And the way that I do that is this is in between C and D, which is the equation that I found. So I would go ask myself, hey, if I set v equal to 0 in that equation, what is x equal to? X should be equal to 11.1875. So we know that this distance is just that 11 value minus 9, which is the amount to the left of it. That makes it easy to figure out what the area of that little triangle is. And we can say, hey, I know that's how much the moment's increasing until I hit my turning point. And I'll do the exact same thing. Hey, what's the area of this triangle? I'm going to end up going down that much. And then finish by figuring out the area that this rectangle has. And that's going to take me down in a linear fashion before I finish at, oh, here we go. Sorry. And we'll see that we're actually still a little bit above 0. And the reason that that is because we have this externally applied moment, if I'm not mistaken. But a good rule of thumb is that your bending moment should start and end at 0 if you don't have external moments applied. So hopefully that makes sense. The biggest thing is to recognize the relationships between shear force and bending moment. So just to have it expressly stated, the area under your shear graph, is going to be equal to your change in moment. And that corresponds positive or negative. And something that we also know is we know if we have point loads or point moments, those create jumps in our graphs, right? But if we don't have a point load or point moment, our graph needs to be relatively smooth. We need to have more of a gradual change. We can't say, hey, we go from here to here without having, say, a point load in between, right? That's just something that can help us make sure that we're actually drawing our diagrams right. The other biggest thing with these problems is just being careful. If you're ever unsure, try actually plugging in values for the beam at that point. Make the cut and see and draw your free body diagram and say, hey, does that match what my graph is telling me? And just making sure that you're being careful with everything. But something that I don't know if I directly pointed out when I was drawing my diagram, but the shear force always looks like the first derivative of the moment, or if you think about it, moment always looks like when you integrate shear force. So if we have a flat line for shear, we have a linear line for moment. If we have a linear line for shear, we have a quadratic or a parabolic for moment. And the other thing that I looked at, I'm going to draw this on another sheet, is if my shear force looks like, this is going to be rough. So if my shear force is going up like this, yeah. So if my shear force diagram looks like that, let's say I've got a distributed load pointing upward and then a distributed load pointing downward. I'm not sure the exact situation, but something along these lines. We know that our moment is going to look quadratic, parabolic. But the question is, okay, this is obviously, how do I want to, yeah. These are both positive, right? So I know I'm just going to keep increasing this whole time. But the question is kind of what is my rate of increase? So we just have to think about how much V is changing. V is only changing a little bit down here as we go this way, whereas up here it's changing a lot more. So what this moment diagram would probably look like is you would start out kind of gradual. You would start out kind of gradual with your change, and then you would go more rapid. And then this would continue rapidly and then slower again, kind of. So I draw that neater after thinking about it. You would start off slow. You would get way quicker changes in the middle, and then you would go back to being slow again, basically, right? So that's another way that you can think about it. And that's how I decided on mine. I said, oh, okay, in this case, we start out gradual and then we get steeper. So if you look at how I drew it, I started out more gradual and then I got steeper, right? Same thing for the little piece, it's just a little harder to see. So that's something else to keep in mind when we're going through these problems.